we're going to look at how the rate constant is affected by temperature. And that's by using something called the Arrhenius equation. And what it does is it links rate constant with temperature and activation energy. And what it looks like is this: K is equal to A e to the power of minus activation energy over RT. So K is the rate constant, and as you know, the units are variable in the rate constant. EA is the activation energy measured in joules per mole. T is temperature, that's measured in Kelvin, not degrees C. So remember, you need to add 273 to convert it from degrees C to Kelvin. R is the ideal gas constant. We learnt this in PV equals nRT. It's given to you 8.31 joules per mole per Kelvin. And A is the Arrhenius constant. So E is an exponential function. So you might have seen this in maths if you do maths. It's E to the power of minus activation energy over RT. So that means if you increase activation energy, so if you look at that, this is at the top of the fraction. So if you increase activation energy, because this is a negative power, if you make EA bigger, the overall number here will get smaller because it's negative. So that means K is going to decrease, which makes sense because if you increase the activation energy of a reaction, the rate should decrease because it's going to be harder for particles to react with the activation energy. And inversely, if you increase temperature, so think again, that temperature is at the bottom of fraction. So if you make that bigger, the fraction is going to get smaller. But because it's to a negative power now, if it gets smaller, the whole value is going to get bigger. So K will increase, which again is something you would expect. If you increase the temperature of a reaction, the rate of reaction should also increase. So another form of this equation looks like this. And because you've got an exponential here, what you can do is you can learn the whole equation. Then you get this equation here. So you don't need to know how to do it in chemistry because it's A-level maths, but just be aware of this equation. So E is known as the exponential and ln or ln is known as the natural logarithm, and both of them are inverses of each other. So to get rid of an exponential, get rid of an E, you would ln the whole expression, ln the whole expression, and if you want to get rid of the ln, you exponential the whole equation. So be aware of this, it'll come up a bit later. Another useful thing you can do with this equation is rearrange it to make T the subject and to make activation energy the subject. So when you do that, you'll get T is equal to activation energy over R in brackets ln A minus ln K, and for the activation energy one, that's equal to RT and in brackets ln A minus ln K. So this is useful when you've got a question asking you to work out one or the other and they've given you all of this information. So it's better understood by doing a question. So let me show you how to use this. Okay, so the decomposition of N2O5 at 308 Kelvin has a rate constant of 1.35 times 10 to the minus 4 seconds to the minus 1. The Arrhenius constant for this reaction is 4.79 times 10 to the 13 seconds to the minus 1. Calculate the activation energy. So for this one, what you would do, because it's asking for activation energy, you're going to use this form of the equation. So EA is equal to RT ln A minus ln K. And what you can do now is sub in these values. So R is 8.31 or 8.314. Times that by the temperature, which is 308 Kelvin. Remember, if it was in degrees C, you'd have to convert to Kelvin. Then you do ln of your Arrhenius constant A, and you subtract that by ln of your rate constant. Okay, so when it comes to learning on your calculator, you'll find it as a button. It says ln on it. So you just press the ln button and then you type in whatever numbers inside the brackets. So if you put this in your calculator, you should get an answer of 103,429 joules per mole or 103.4 kilojoules per mole. So that's how you'd use that equation. Now, another way you can use this equation is to write it in a form that produces a straight line graph. So let's look at the ln version of the Arrhenius equation, and I'm going to write this in a different way. So it's going to be ln K is equal to, and what I'm going to do is I'm going to separate out the activation energy in R from the T. So what you can rewrite the second term as is EA over R with a minus in front times by 1 over T. So what you can do is you can open out these brackets and you should end up with the same thing. And then the ln A you just add on at the end. So what you've got here is just the same equation but just written in a specific way. The reason I wrote the equation like this is because it's now in the form of y is equal to mx plus c, which is basically, if you remember from Maths GCSE, the equation for a straight line. So what that means is on your graph, if you plot y against x, then your m would be your gradient and your c would be your y-intercept. So if we translate this to the equation we have above, if you plot ln k against 1 over t, like so, then you should get a straight line graph. Now activation energy is positive, R is positive, but this has a minus sign in front of it. So that tells you that the gradient of this line that you're going to plot is always going to be negative. So it might look something like this. And what you can do is once you've plotted a graph of ln k against 1 over t, is you can work out now what your activation energy is going to be from your gradient and what your Arrhenius constant is going to be from the y-intercept. So in an exam, they might give you values and they might ask you to plot a graph of ln k against 1 over t. So your y-intercept would be this point here. So you get that point there and you know that that point is ln A. And from your graph, you can also work out the gradient, which you know will be, according to this equation, minus activation energy over the ideal gas constant. So let's say, for example, we plotted a graph and we worked out what the y-intercept is, so where it crosses the y-axis, and we got a value of 3.1. And we worked out the gradient by doing the change in y over change in x, and that gave us minus 2.2. So from that, we can say that ln A is 3.1 because that's the y-intercept, and minus activation energy over R is equal to minus 2.2 because that's our gradient. And from that, you can calculate what the Arrhenius constant is and what the activation energy is. So for the Arrhenius constant, you need to move your ln to the other side. So remember earlier I said that the inverse of ln is e to the power, or the exponential function. So what you'll do is A is equal to e to the power of 3.1. That's how you get rid of your ln. And when you do that, you put it in a calculator. So you look for the exponential button on your calculator and then you type in 3.1 and you should get an answer of 22.2. And to work out what the activation energy is, first of all, you can cancel out your minus signs. And you just do 2.2 times by 8.31, which should give you 18.29. So that's how you use a graphical method to work out activation energy, or the Arrhenius constant, from the Arrhenius equation. For more videos like this, summary videos, worked examples and exam tips, subscribe to my channel.